my name is David Lee Jr. and this is my Lab 3, Mass of a Black Hole. Just going over the table of contents. We'll start with an introduction to the experiment, then start with the computational models, and then answer what if and what does it mean. So, like the past two models, one of the key concepts is Newton's second law. This is going to help us predict the motion of the star's motion around the black hole. And V final is equal to F net times time divided by mass plus VI, and then R final, which is position, is equal to V average times T plus RI. Another key concept is the parallel and perpendicular components of the net force. The parallel component, which can be shown on the left screenshot, points in direction of motion. It is related directly to change in speed of the object. The perpendicular component points to the center of the turning circle and is related to change in direction of the object, and that's on the right. Another key concept is universal gravitation, which is the force of an object due to an attractive force, which can be defined as F is equal to G times mass 1 times mass 2 divided by r squared, where r squared is the radius of the distance between the two objects. And then also have the two different free body diagrams. In part 1, the mass of the black hole and the sun are the two different objects that we are observing. The black hole is the surroundings in space in general, and then the star is the system. And then in part 2, we have three objects we are concerned with: the planet, the black hole, and the rocket ship. And then the different arrows are showing the different ways that the gravity is impacting the different objects in the surroundings. And in this case, the rocket is the system. To build a computational model, these are the initial conditions for part 1. So we have gravitational constant, this mass of the star, the time interval, and then the time for the first observation data point. To build a model, I had to make sure that I would calculate the dp dt parallel and perpendicular, and edit other parts of the starter code to ensure I created the appropriate model. I'll also apply Newton's second law to compute the initial and final momentum vectors. And then also use Newton's second law to calculate the perpendicular, F net perpendicular and F net parallel. And finally, I needed to make sure I calculated the mass of the black hole using all the data we had gathered, and that's on the left. Video of the computational model. My results resulted into the net force magnitude was 8.77975 e to the 28th. Parallel component was 1.11084 e to the 20th, and the perpendicular component mag was 8.715 e to the 28th. For the mass of the black hole, it spits out different values for each iteration, so I calculated the average to find the mass of the black hole. Just an analysis of part 1. The star's oval-like orbit is influenced by the gravity of the black hole, also known as universal gravitation. The further the star is, the lesser the magnitude of the gravitational force, and vice versa. The changes in the parallel and perpendicular components model the changes in speed and direction, respectively. And some possible errors could be rounding errors when iterating, or rounding for the gravitational constants, and also rounding when calculating the average. That would explain the different results for each iteration. For part 2, we were trying to figure out the initial speed to break the orbit of the black hole. So I updated the mass of the black hole with the result of part 1 in the lab, left everything else the same. And then we needed to make sure that we're still applying those same concepts and the same key concepts of Newton's second law and the parallel and perpendicular components of F net, and basically just use to find the distance between the planet and the black hole, then the planet between the ship, and find the F net on both the planet and on the ship, and then use those values to find the velocity of the planet and the velocity of the ship, and make sure we're updating the ship's position and the planet's position. This is the video of the second computational model. The only way to find the speed to escape the black hole was through trial and error. So through trial and error, I was able to find that -6 e to the 7 in the x direction and 1.8 e to the 6 in the y direction was the closest I could get to the black hole while escaping the system, and that it was slingshot around the black hole due to gravity. And then it's also the same types of errors in terms of rounding errors, but also the initial velocity we could only find through trial and error. So maybe this isn't the exact closest that we could get to the black hole. So answering what if, how are the net force and its parallel and perpendicular components different from the rate of change of momentum and its parallel and perpendicular components? Net force is equal to the momentum's rate of change, and the parallel and perpendicular components are equivalent to what's shown in the screenshot in the bottom. But we can also use rate of change of momentum to find the net force, while we would need the mass to find the net force. What initial velocity would your spaceship need to have in order to enter into some kind of orbit around the black hole? This was another case of trial and error. I plugged in different values until I could get an orbit that would somewhat mirror the same shape as the planet. And to get this, I got -7 e to the 5, 1.1 e to the 7, and 0. Thank you for watching.